Now we will have Norbert, who will be presenting a paper on pseudo-random number generators based on a modified Riemann zeta functions. Go ahead, Norbert.
Okay, thank you very much. Welcome, everybody. I would like to make a presentation regarding to the Riemann zeta function and some random number generator. This is a joint work with Bertrand Borchos from the Eötvös-Loránd University. And regarding to the Riemann-Siegel function, it's also a joint work with Professor Attila Kovács. We have been studied the Riemann-Siegel function many years ago, started, and many interesting behavior can be expected from this function. And we would like to show how to use or show some idea how to use as a random number generator. So what is the main motivation? Of course, to create high quality, uniformly distributed random numbers. And this is interesting because, of course, it's like this is a randomness extractor. So if you have some weak entropy source, then you can use this function to generate more uniformly distributed random numbers to create high quality random numbers. And of course, it's really important to emphasize that we would like a lot of important criteria for this function, like fast to compute. And of course, statistically, it should be indistinguishable from true random sources. And it should be, there is no relation between the consecutive values. So there should be no any correlation. And of course, we try to not use the random number generator outputs to avoid short cycle length. I'm going to show you what does it mean exactly. So basically, this random number generator is based on some digit expansion. Maybe you're familiar with that there are many random number generators that try to do digit expansion. You can see, for example, the first one, when you try to do some digit expansion from irrational numbers, it's a really good thing. However, it's really infeasible to calculate. Just imagine that square root of 2 and you have to calculate millions of digits. It's really slow and really infeasible to calculate for high precision. Using simple functions, of course, it's weak against cryptographic attacks, so it also cannot be used. And surprisingly, there are simple functions, 1 over n, for example. However, this is possible to attack by continued fractions, as Blum and Shub shown that is it possible to recover the secret n in polynomial time only observing a few bits. Few bits means there is a specific bound. What does it mean? So basically, the next things when you have to think about that, of course, we would like to avoid the continued fraction attack, and maybe there is a chance to use algebraic numbers. However, this is also the very famous Lenzler-Lovász algorithm. It can be used. Lenzler-Lovász showed how is it possible to find, for example, peaks in a deterministic polynomial time if you would like to predict the future bits of some alpha complex number. And basically, this kind of attack, it's really important to know that it's because this attack, many digit expansion random number generator is not working. I mean, for cryptographic purposes, it's not okay, and many such kind of attacks exist. And the last attack, I would like to just introduce the Stehlé approximation. That it's really interesting to consider some random number generators as approximation, and we are really interested in this aggregation, as you can see, number 1 aggregation, and a special case of this problem when some bits is hidden from the output of the random number generators. Of course, for example, you have an LCG, you have any kind of random number generators, and this is natural to hide some bits from the output in order to hide the original function, in order to hide the original behavior of the function. However, as you can see also, regarding this Stehlé approximation, is it possible to find the future bits and find all of the solution for this aggregation if some integers and some observable bits is known from the random number generator outputs? So basically, the main motivation was to try to make some digit expansion random number generator that is currently not known any cryptographic attack. However, it is based on number theoretic hardness problem, or it's related to some distribution of the prime numbers or any mathematical programs. It's really hard to understand. I mean, really hard to solve. And as you can see later on, it's really hard to understand the behavior of the function. And this was the main motivation when we studied these kind of Riemann-Siegel functions that maybe it's possible to use for random number generations. And it has turned out in the last few years that it's really promising how to use and how to make fast random number generators. I'm going to emphasize at the end of the presentation, what does it mean fast? And of course, comparing to arithmetic operations, random number generators, we can see the benefits and we can see the what is better or what is not. So basically, the general construction is really simple. You have a secret seed, for example, 2 power of 128 bits. And in this situation, you have a secret seed. And in every step, you are applying a function. You just extract some digits, and we have an output. And we can increment the state. The operation is almost same, you know, like in a block cipher in counter mode. So the ideal f function for us is fast to compute, of course. Fx is irrational for all x. Fx is continuous and not periodic. Not periodic is very important for us in order to not to predict the future bits of the generator. Not a one-to-one function. The inverse of f does not exist. And of course, finding the approximation for f, it should be hard. There are many attacks based on like Coppersmith attack or like the Stehlé attack that when we try to approximate the function and we try to figure out what is the next state of the random number generator. And of course, for a given y, there is no efficient method known how to find an x such that fx equals to y. This is such kind of statement like in the hash functions. So basically, if you think about the general construction, Dirichlet-L function of the form you can see in equation 3, it's really good for our purposes. And namely, we choose the Riemann zeta function. And the Riemann zeta function can be defined an infinite series. Why we choose the Riemann zeta function? I'm going to show you that we studied very well the Riemann zeta function, and there are many number theoretic theorem regarding to this function that is regarding to the distribution of the prime numbers. So the behavior of the function is still unknown today. We have a lot of knowledge about the function. We have known many things about the function. However, there are many things that we are not able to solve today. So for example, the distribution of prime numbers, it's a simple question. However, many interesting behavior can be deduced from this function, and it's more than enough to use as a random number generator. As you can see, this is a complex function. So we would like to eliminate the time-consuming calculation. So we are not using the exact Riemann zeta function. We are using the Riemann-Siegel Z function or Hardy function. So this is, if you can say, this is only calculating the Riemann zeta function on the critical line. So this is not a complex valued function. So it's much better to use it for our purposes. And you can see the complexity of the function. It's still not enough for us. I mean, it's really slow. And you can see when we try to calculate the Riemann-Siegel theta function and the whole sum, the function, it's still slow for us. However, as a random number generator, it's really good. But we have to do something in order to get a much better function. So before I'm going to introduce what function we choose, let's just see this example. Choose a random number. This is our secret seed. For example, 2 power of 128. And we just would like to determine the sign of the function. You can see this is negative or this is positive. So basically, we have to calculate the whole time-consuming sum in order to calculate the sign of zeta s. So it means that if somebody just pick a random number and try to calculate that in this particular position, the function is positive or negative, we have to calculate the whole function. There are some prediction, but certainly we can say that the function at that height is positive or negative if we calculate the whole sum. You can see the interesting behavior of this function. So basically, the main idea was just try to imagine the secret seed, and we try to extract some bits. For example, this first secret seed, we extract 0. The second one is 1, 0, 0, 1. We just incrementing the secret seed. Of course, in this particular format, this function is really slow. So we just want to make much faster, because every step we only extracting 1 bit. Of course, it's slow. However, we can prove, and it's possible to prove that it's, in order to predict that it's 0 or 1, this is a really hard mathematical problem. And of course, we try to avoid that, for example, after each particular, when we are incrementing the secret seed, we try to avoid that it shouldn't be produce only zeros or only ones, of course, because it's not good for random number generators. So what happens if there are no sign changes between 2 zeros? For example, for x plus 1, x plus 2, x plus 3, x plus n, we get always 1 or always zeros. I mean, the function producing the same sign. So if somebody would like to observe such interesting things, is it possible to observe a behavior of the zeta function like this? You can see that the local maximum of the function, for example, here in the first position is positive. Here is the local maximum is negative, positive. So basically, you can see that between 2 zeros, there was no sign changes of the function. So it can produce interesting behavior. Hopefully, it shouldn't be happen. What does it mean it shouldn't be happen? Regarding to the Riemann hypothesis, the Riemann hypothesis is equivalent to the statement that all local maxima of the ZT are positive and all local minima are negative. For us, it's really important because we shouldn't observe such a behavior for ZT. And as I mentioned to you, this behavior shouldn't expected. So when we just try to this one, incrementing, for example, the secret seed by 1, is it possible really to get zeros and ones? And basically, this is one of the main idea that there is not no method how to predict the sign of the ZT function, and it's correlated to the distribution of prime numbers, to the Riemann hypothesis, and it's really hard to expect the behavior of the zeta function. Of course, we still didn't solve the problem that it's really solved, and only extracting 1 bit in every position, it's too slow. So basically, of course, there is an algorithm from Hiary that it's possible to compute the Riemann zeta function much faster than the original Riemann-Siegel formula. However, this is still too slow for us. So we just introduced a new function in the last few years, and this function can be used for random number generators. The new function has the same behavior like the zeta function. However, it is much easier to compute, and we expect with the same behavior. You can see, we just recall the Riemann-Siegel formula. You can see the sum that we have a lot of sum to have to do. However, we introduce the same function, almost the same function. However, we are going to logarithmic of t. So it's, you can see that ordo log t, only the time complexity of the ft function. So this ft function, it has turned out that it has the same interesting real behavior than the zeta function, however, really fast to compute. There is a comparison, for example, if somebody would like to compute the zeta function, the original zeta function, 10 power of 30, for example, at the height, 10 power of 30, like the line number 5 here, it takes 60,000 seconds, 20 hours. So it's it's not good for random number generators. However, we can see that it's less than 1 millisecond with the same architecture. It's a normal computer. It's a 2017 MacBook Pro. We can see that the same amount of computation for FT. It's a magnet of order of magnitude less than the zeta function. And of course, 10 power of 100 or 10 power of 1000, it's not possible to calculate the zeta function because it's too time consuming, and even with supercomputing cluster, it's not possible. However, the FT function, it's really easy to compute. And I would like to emphasize again that we deeply investigated the behavior of the FT function, and it's really correlated to the zeta function. So the unpredictable behavior can be seen here. For example, one would like to calculate for a secret seed the function. We are incrementing the secret seed. And of course, for example, from the digit 4 or digit 5, we can extract some bits. Of course, in every step, we can extract more bits or more digits in every iteration. And the function is much faster after that. You can see that here, for example, if the function is negative, we are drop the first 4 digit. If the function is positive, we are drop the first 5 digits. So we just try to implement the weird behavior of the ft and zeta function that we cannot predict when the f function is negative or when the f function is positive. Basically, our main idea was regarding to not to use the L-cube algorithm and not to use to any approximation regarding to this function. So we just truncated the function, and we are only using the fractional part. Why is important for us? Because it has turned out that if somebody is able to observe that, for example, it's -2, -4, or it's 16 or 7,000, the height of the f function and the zeta function, somebody can predict how large is the secret seed. So regarding to the Lindelof hypothesis, this is how the zeta function is growing. It suggests us that if somebody can observe the output of the zeta function, for example, the zeta function output is 10,000, we know that it's not possible that 10 power of 2 or 10 power of 3 was the input, because the zeta function is increasing much slower. So it means if somebody can observe that the output is 10,000, we should approximately in the height 10 power of 30. So in this case, the best scenario is to drop the integer part of the function, and we are using the fractional part. So only we can observe the fractional part of the function, and it's not possible to reverse the original function, and it's not possible to predict how large was our secret seed. I mean, it's really important not to know that the secret seed is 2 power of 128 bits or 256 bits. Of course, the zeta function is very likely. We have shown that how to predict where the zeta function is really large. And to be honest, the whole research is not started with random number generation, but the whole research started a few years ago in order to predict large zeta function on the critical line. So it was a number theoretic problem. And we were able to solve this problem using Diophantus approximation. So using Diophantus approximation, one can predict how large is the zeta function, and or ft function can be used to predict where the zeta function is have a peak values or not. So to avoid this one, of course, everybody knows or heard about the very famous Rensler-Lovász algorithm, it's possible to use the same algorithm in order to generate some very interesting candidates where the zeta function is really likely to be will be very large. So using the Rensler-Lovász algorithm, one can produce inputs for this function and predict that the function should be large or should be small. We also use the same for this FT function to solve some simultaneous Diophantous approximation problem. And it has turned out that if somebody can predict some special values of the zeta function, then it's really easy to predict where the zeta function is large. And the whole research started because we wanted to find large zeta functions. And meanwhile, when we were doing this, we just realized that it's not possible to do this. It's not possible to create the same theorem for different irrationals. I mean, for multidimensional irrationals. So it's really hard to approximate the zeta function for many irrational functions. And basically, this is the second idea when we use this. And this is the main reason why we would like to drop the beginning of the output. And we are using only the truncated fractional part of the zeta function in order to not to use any Diophantous approximation to predict what is the output of the zeta function. Using this technique, we were able to calculate the largest known zeta value and on the critical line. However, this was not regarding to random number generators. After that, we realized it's not possible to solve by the Rensler-Lovász algorithm. It's not possible to solve by only using Diophantous approximation to predict how large is the zeta function. And also the sign that is positive or negative. It's really hard to predict. And it has turned out that it's true also for the FT function. FT can be calculated really fast, and the FT function is really good for our random number generator choice. So basically, here is pseudocode of the extractor. You have any seed, for example, a secret seed. Of course, this can be arbitrarily large. We just use the mod 2 power of 128. And you can see line number 6 and line number 7, line number 8 and 9. That's we just try to, if the f function output is negative, then we are using a different index. If the f function is positive, we are also using a different number. So we just use this one. As I mentioned to you, we are using the fractional part of the function in order to not to do any attack regarding the Stehlé approximation, the L cube approximation, and not to predict what the height of the seed, what is the output of the f function. And basically, to avoid any correlation between ft and ft plus 1, as you can see in line 11, we just used some arithmetic operation. However, this is not necessary. This is only just for research purposes. Without this one, the function is still pass the NIST test, the test U01 big crash test. But however, in order to, as I mentioned to you, we really don't know any correlation between ft and ft plus 1. However, maybe in the future somebody is connecting the ft function, the zeta function, and found some interesting distribution between the prime numbers, and it would be totally useless. However, assuming the Riemann hypothesis, this is a really hard problem to do this. And you can see the last line, line 13, we just incrementing by 1 the seed. However, another really important note that if we are choosing the step size, for example, for 88, this is the logarithm of 2 power of 128, then this is also related a very famous problem that we cannot predict that the FT function is positive or negative. Basically, you can see in this picture, these slides, the NIST test that's with statistically tested, the output of the random number generator. It's passed all the statistical tests from NIST, and also passed the test U01 big rush test. And basically, if somebody only generating values, as I mentioned previously, 0, 1, 0, 1, only observing what is the sign of the function, so it's negative or positive, this is still past the NIST test. Of course, this is too slow, so this is the reason why we introduce the FT function, and also this is the reason why we extract in one step more than 1 bit in order to speed up the random number generator process. So basically, everybody is looking for the performance, of course. I think this is the last thing what I would like to emphasize. In 2014, when we tried to find the largest Riemann zeta function, we implemented this for the GPUs to do Diophantus approximation and calculating the Riemann zeta function. And we use quadruple precision library. We use the Karatsuba multiplication algorithm, and we achieved 100 megabytes to 300 megabytes seconds random data that can be generated. As you can see in the CPUs, for a modern computer like a MacBook Pro from 2017, it's 100 megabyte data. It took almost 20 seconds. So basically, you can see that comparing to another functions, it's of course obviously much slower. So basically, to summarize, we would like to we wanted to create some random number generators that can be assuming, for example, the Riemann hypothesis. Only observing the output is really hard to predict what was the input, and we wanted to create some function that is really hard to approximate, even with Diophantus approximations techniques. And of course, we wanted to create a function that it's possible to pass all of the known statistical tests. Of course, we can see that the running time of the generator is efficient enough to use in practical life. However, it cannot compare to other random number generators that are based only arithmetic operations. Of course, it's much slower. But we can see that maybe there are some benefits that can be used, and there are some interesting things of the functions and also the Dirichlet-L functions that can be proved, and it's really interesting research.
Thank you, Norbert. Thank you for the interesting talk. We have 2 questions from Raghavendra, Norbert. The first question is: it is infeasible to go through all secret states for checking the unpredictable behavior. How many seeds did you consider to have confidence in security of your PRNG, or do you have any theoretical proofs?
Yeah, this is a further research. So it's really important when we, for example, we have a seed with low entropy, and we would like to check that what's the difference between a high entropy seed and a low entropy seed. So we started with very low entropy seeds, but to prove that there is no difference between a low entropy seed and the high entropy seed, it's not ready yet. So it's and maybe there is no chance to prove it that there is a difference between them. However, assuming the Riemann hypothesis, it shouldn't be, but right now there is no mathematical proof that there is no weak seeds.
The second question, Norbert, we can answer it fast. Did you compare the PRNG performance with real-world stream ciphers such as Grain and Trivium?
Yeah, we compared many stream ciphers, and as I mentioned to you, that most of the stream ciphers and most of the block ciphers based random number generators are only using arithmetic operations, bitwise operations, and so on. So it's not necessary to compare because it's much slower, as we can see in the last slide. For example, for a MacBook 2017 to generate 100 megabytes, it's almost took 20 seconds. It's enough to use in practical life. However, it cannot compete with other random number generators. So yes, we would like to emphasize that this is not the fastest random number generator.
Thank you, Norbert. There's one more question from Hamad. I will leave you to answer it offline since we are a bit tight on time. We give you a virtual round of applause. Thank you very much, Norbert. This was a very interesting talk.